The universe is full of mysteries, but none is more intriguing than the ones that lie in its distant past. How did the first galaxies form and evolve? What secrets do they hold about the origin and fate of the cosmos? These are some of the questions that NASA's James Webb Space Telescope is trying to answer by peering into the deepest and darkest regions of space. And now, what it has found is astonishing. 10 galaxies that might be older than the universe itself. How is this possible? Join us as we delve deeper into this mind-blowing discovery. The James Webb Space Telescope, launched in December 2021, was a monumental achievement for astronomy and cosmology. It was designed to peer into the deepest and darkest corners of the universe and to reveal the secrets of its origin and evolution. In June 2022, it made its first stunning discovery when it took its deep field image, a long exposure of a patch of sky that captured the faintest and most distant galaxies ever seen. Suddenly, galaxies started to pop out from the darkness of time and space, revealing themselves. And now, the JWST has discovered there are about 10 more galaxies that could be even older than Maisy's galaxy. How is this possible? How did these ancient galaxies form and survive in the early universe? And what do they tell us about the history and fate of our cosmos? Keep watching to find out. But first, let's talk about the amazing discovery of Maisy's galaxy and why it's so important for our understanding of the universe. These galaxies emerged from what we believe to be the universe's dark ages, a period of time when the first stars and galaxies formed out of the primordial gas. This discovery challenged our current models of cosmic evolution and raised doubts over the validity of our scientific theories. And it wasn't just a couple of galaxies. The Webb telescope found hundreds of them, each with its own story and history. One of these galaxies was found by an Austin astronomer, Stephen Felstein. He named it Maisy's Galaxy and dedicated it to his daughter because they spotted it on her birthday. Initially, the scientist and his team thought that the galaxy had formed almost immediately after the Big Bang in cosmic timescales. They estimated it to have been around only 290 million years after the Big Bang, making it the oldest galaxy ever observed. But after analyzing the galaxy with more advanced equipment, they found out that it's about 100 million years older than that. For reference, the universe as a whole is about 13.77 billion years old. That means that the galaxy was born only 190 million years after the Big Bang, when the universe was still very young and hot. Maisy's galaxy still holds the record of being the oldest galaxy ever observed, but it might not be the only one of its kind. Currently, the JWST has detected about 10 more galaxies that a team of researchers, CHEERS, Cosmic History of Early Epoch Reionization Sources, is now evaluating, which could be even older and more massive than Maisy's galaxy. But how do we know how old these galaxies are? And how do they challenge our existing theories and models of how the universe was formed? To answer these questions, we need to understand how the JWST works and how it differs from previous telescopes like the Hubble Space Telescope. The JWST is a marvel of engineering and science, with a 6.5-meter primary mirror that can collect more light than any other telescope, and a suite of 4 instruments that can observe the universe in infrared wavelengths. The JWST is also located at a special point in space called the second Lagrange point, or L2, where it can orbit the Sun in sync with the Earth and avoid the interference of the Earth's atmosphere and heat. The JWST's infrared capabilities are crucial for studying the oldest galaxies in the universe, because they are so far away that their light has been stretched and redshifted by the expansion of the universe. The redshift is a measure of how much the light from an object has been shifted to the red end of the spectrum due to its motion away from us. The higher the redshift, the farther away and the older the object is. The JWST can measure the redshift of these galaxies using a technique called photometry, which analyzes the brightness of light in images using a small number of wide-frequency filters. By comparing the brightness of these galaxies in different filters, the JWST can estimate their redshift and their age. The JWST's redshift measurements have revealed that some of these galaxies are older than Maisy's galaxy. In fact, some of them may have formed when the universe was only a few hundred million years old, shortly after the Big Bang. In the words of Fabio Pacucci of the Harvard-Smithsonian Center for Astrophysics, we're seeing a rise of massive galaxies faster than we previously thought. This is astonishing because it means that these galaxies formed when the universe was still very hot and dense, and when the first stars and galaxies were just starting to light up the universe. These galaxies are also very massive, with billions of solar masses, comparable in weight to the Milky Way, but packed into structures 30 times smaller. The first among them may be a class of galaxies identified by a team of scientists at the Swinburne University of Technology in Australia. The team found galaxies with billions of solar masses, comparable in weight to the Milky Way, from just an estimated 750 million years after the Big Bang. These G galaxies are 10 to 100 times bigger than galaxies previously seen in this era, and are packed into structures 30 times smaller than the Milky Way. What is more intriguing is that the galaxies seemingly are hosting many more stars than we thought would be possible. Indeed, the very fundamentals of our understanding of how massive structures build up over time have challenged the cosmological standard model. According to our standard model of cosmology, galaxies form and grow in the presence of dark matter, a mysterious substance that makes up most of the matter in the universe, but does not interact with light or normal matter. Dark matter forms large structures called halos, which attract normal matter and gas, and provide the seeds for galaxy formation. The first stars and galaxies are thought to form in small halos, and then merge and grow into larger ones over time. This process should take billions of years, and should result in galaxies that are smaller and dimmer in the early universe, and larger and brighter in the later universe. But the JWST's observations of these ancient galaxies challenge this picture and suggest that there might be something wrong with our theory of the creation of the universe. Not only did the team discover more distant G galaxies, which are the brightest and most massive galaxies in the early universe, but they also detected some Milky Way-like galaxies at the edge of the cosmos that, according to our current physics, should not exist. These findings reveal the diversity and complexity of the early universe when it was only a fraction of its current age. Many of the galaxies that the JWST observed were rich with glowing gas, so bright that the gas itself could outshine stars. This indicates that these galaxies were undergoing intense star formation, creating new generations of stars from the primordial material. Observations now reveal that almost 90% of the galaxies had so-called extreme emission features, meaning they exhibited all that glowing gas. These are the shimmering infant gassy galaxies that dominated the young universe when it was around only 2 billion years old. But among these gassy galaxies, there was one that stood out from the rest. It was a galaxy that looked remarkably similar to our home galaxy, the Milky Way. Yes, you heard that right. When the universe was just 2 billion years old, the newfound spiral galaxy Sears 2112 appears to have featured a bar of stars and gas cutting across its heart. This is a surprising find, as galactic bars are thought to be a sign of maturity and stability in a galaxy. They are structures that rotate cylindrically, funneling gas into the galaxy's center and sparking bursts of star formation. Astronomers previously thought that this galactic structure marks the end of a galaxy's formative years, so it was expected to be seen only in old galaxies that may have reached full maturity, perhaps those that existed halfway through the evolution of the universe. And with the Hubble Space Telescope's past observations of galaxy shapes, we thought the early universe hosted very few barred galaxies. However, everything that we know about the early universe is changing. The new findings gathered from data by the Webb telescope conclude it may not be necessarily true that barred spirals must have existed only recently in the universe. The discovery of spiral galaxy Sears 2112 reveals galaxies that resemble our own already existed almost 12 billion years ago, when the universe was just 15% of its current age. Yes, Sears 2112 is observed at a redshift of 3 when the universe was 100 million years old. Essentially, this means the light from the galaxy took almost 12 billion years to reach the James Webb Space Telescope. This discovery also challenges our standard model of cosmology, which predicts that the early universe's physical conditions must have prevented the formation of such barred galaxies in general. But here we are. Not only that, even theoretical predictions from cosmological simulations really struggle to reproduce such systems at those epochs. Now, scientists believe that 85% of all matter in the universe is dark matter, a mysterious substance elusive to observations because it doesn't interact with light at all. Dark matter is thought to have played a crucial role in galaxy formation and evolution, shaping the distribution and structure of galaxies from as early as 380,000 years after the Big Bang. However, a new discovery by the JWST team shows that galaxy evolution, at least in the case of CEERS 2112, was dominated by ordinary matter and not dark matter when the universe was about 2 billion years old. CEERS 2112 is the name of the spiral galaxy that resembles our Milky Way, which was found at the edge of the cosmos by the JWST. This galaxy is remarkable not only for its shape and structure, but also for its composition. According to the new findings, this galaxy was mostly made of baryons, the ordinary matter that you and I and everything we see are made of, and not by dark matter, despite its overabundance in the universe. This is a surprising and important discovery, as it challenges our understanding of how galaxies form and evolve in the early universe. It suggests that there may be other factors besides dark matter that influence galaxy evolution, such as gas dynamics, star formation, and feedback processes. It also raises questions about how common or rare such galaxies are in the distant universe, and what implications they have for our cosmological models. This discovery is one of the many breakthroughs that the JWST has achieved since its launch. The JWST is the most powerful and sophisticated space telescope ever built, designed to explore the origins of the universe, the formation of stars and planets, and the search for life beyond Earth. The JWST is able to observe the faintest and most distant objects in the universe, using infrared light that can penetrate dust and gas clouds that block visible light. The JWST team is excited and amazed by the new discoveries that the telescope is making every day. Co-author Jairo Abreu, who is a researcher at University of La Laguna, said, "At this point, I don't think anyone is expecting anything other than new from the James Webb Space Telescope. It is a game changer for astronomy and cosmology, and we are just getting started." In light of this, scientists are of the opinion that the James Webb Space Telescope could soon solve mysteries of the Milky Way's heart. Ever since astronomers first laid their eyes on the sparkling spiral arms of our home galaxy, the Milky Way, they have wondered what processes might drive the evolution of these massive star-studded structures. Presumably, those same processes are why we see such a stunning diversity of galactic neighborhoods in the observable universe, which contains an estimated 2 trillion galaxies with unique sizes, shapes, and compositions. The center of the Milky Way, also known as the galactic center, is one of the most studied regions in the night sky, but it also hides many secrets. One of the biggest unresolved questions about the Milky Way surrounds how its supermassive black hole, star A*, affected our home galaxy's evolution. A star A* is a monster that weighs about 4 million times the mass of the Sun, and it lies at the very core of the galaxy. It is surrounded by a dense cluster of stars, gas, and dust, some of which may fall into the black hole and feed it. Astronomers already know that supermassive black holes like star A*, grow mostly by feeding on gas that surrounds the holes themselves in plate-like shapes known as accretion disks. Thus, because the presence of such gas is also a necessary ingredient for star formation, it is reasonable to infer a relationship between the growth history of Sagittae A*, and the rate of star formation in the galactic center. The proposed multi-epoch observations of the galactic center by the JWST should give astronomers a solid idea of how many stars are forming, and therefore the rate of growth of star A*. However, star A** is not a typical supermassive black hole. Unlike some of its counterparts in other galaxies, which emit large amounts of electromagnetic radiation as they devour material, star A** appears to be relatively quiet on this front, suggesting it isn't consuming large volumes of material. Astronomers refer to SGAR, A** as a quiescent black hole, which means it is basically dormant, which is a clue in the story. SER. A** is a quiescent black hole and appears to have acquired most of its mass in the past. Rainer Schödel, an astronomer from the Instituto de Astrofísica de Andalucía in Spain and first author of the paper, told Space.com. This implies that SCAR A** may have had a different impact on the Milky Way's evolution than other supermassive black holes. It may have been more active in the past, when the galaxy was younger and more turbulent, and then slowed down its activity as the galaxy matured and stabilized. This could explain why the Milky Way has a relatively thin disk and a well-defined spiral structure, unlike some other galaxies that have been disrupted by their black holes. Another aspect of the galactic center that the JWST could help illuminate is the distribution and types of stars that populate it. The JWST is able to observe the infrared light that can penetrate the dust and gas clouds that obscure the galactic center in visible light, revealing the hidden stars and their properties. Ginsburg explains that the survey could help astronomers get better estimates of something called the initial mass function, IMF, which is the relative number of big to small stars that form. The function tells astronomers how much light star populations produce. This is important in studies of galaxies too far away for astronomers to see individual stars. The JWST is an extremely competitive telescope. With what may be the highest oversubscription rate of any telescope ever made, astronomers are asking for a lot more time than is available, Ginsburg said. That is why the astronomers who study the galactic center have formed a consortium to propose a comprehensive survey of the region by the JWST. The consortium includes more than 100 scientists from 16 countries, and they have published a white paper outlining the scientific goals and methods of the survey. The white paper also serves as a way to show the astronomy community that there is broad consensus on the need for such a survey, as there are some challenges in getting the proposal approved. One of the challenges is that the galactic center is a very popular topic among astronomers, and many of them want to participate in the JWST Galactic Center surveying program. However, there are rules that say if you're on a proposal, or if you would benefit, then you cannot evaluate the proposal, for good reason. This creates a problem for the community that studies the galactic center, as almost all astronomers who study this region want to participate in the JWST Galactic Center surveying program. That leaves nobody with the specific knowledge required on the topic to fairly review the proposal. It was therefore important to show the astronomy community that there is broad consensus on the need for such a survey, says Ginsburg. The Milky Way's galactic center is the only galactic core we can observe where each star can be investigated individually. And the more we learn about our galaxy, the more we will learn about how other galaxies evolve throughout the cosmos.